Okay, let's start our lecture number 11, and we are going to look into the method of images. In principle, we are going to talk about the method in general, and we are going to apply it for a planar boundary. This method is interesting because we can use it to know how to build Green's functions, how to construct Green's functions for different boundaries. Okay, we are going to construct today the Green function for a planar boundary and an arbitrary charge distribution nearby this boundary. So to do that, we are going to look into the method of images. We're going to talk about the principle of the method, what is the general scope of the method, and we're going to consider a couple of cases just to show some features when you have a charge nearby a conducting surface. We're going to talk about very simple problems in which you have a point charge enclosed by a spherical shell, a spherical conductive shell. And what happens when we establish different conditions on this charge position, let's say, and what happens inside and outside of this spherical shell. Then we go to, after you do that, because these examples we're going to talk about are very nice for us to understand the concept of shielding, okay? And how we are going to address method of images for other types of surfaces different than planar surface, curved surfaces. So after we do that, we are going to explore the method for the case of a point charge nearby a planar conductor, and then we are going to show how to determine the solution of Poisson's equation in the hemisphere based on the solution of a point charge. We're going to extend the procedure to include an arbitrary distribution of charge nearby the planar surface. Then at the end of the class, of the lecture, we are going to talk about how to construct the Green's function in the hemisphere. In other words, giving the potential an arbitrary information of the potential on the plane z equals 0, and let's say that the potential vanishes far away from the plane. What's the general solution for an arbitrary charge distribution on this hemisphere, given this prescribed potential on the plane z equals 0? Okay, so references for this class, we have our ebook. We outline the procedure, and we go also chapter 2 of Jackson, section 2.1. So the idea of the method is that outlined in this picture, you have this diagram here in which you have a boundary of an arbitrary shape represented by surface sigma, and you have a set of n point charges, right, inside of this volume. Could be outside as well, but let's start with an inside problem. Given the potential on the boundary and given the locations and values of these point charges, what is the solution inside? That's the question, right? If we can do that, we can assemble several point charges, we can make it then very close, and we can form a continuous space charge distribution, and so an equivalent problem, right? So the idea, and let's say that this medium is homogeneous with a permittivity epsilon. The idea is just to ask the question, well, suppose that we add some fictitious image charges they are fictitious, so they have to lie outside our domain. So they are those blue dots here, right? So they are outside the domain that is inside. Our domain is inside of the boundary, the region enclosed by the surface sigma. So the question is this: is it possible to find a set of M image charges that equilibrate the potential in the boundary? That's the question, right? If we are able to find the location and values of those sets, of this set of M charges, then if we satisfy the boundary condition, uniqueness theorem guarantees that we have a unique solution inside of the region, in the domain, okay? Let's see how that works, okay? Let's see if that's true, right? So, let's assume that this is the original set of charges. And also we specify the potential on the surface. Let's call it a function of the coordinates on the surface, a function that's called phi 0. So we add those, let's label those real charges qi, small case, lowercase, and the location xy. I is a discrete variable that goes from 1 to n. Then we add those capital Q charges, qj, with j going from 1 to m. So m charge. Location of the original charge xi inside of the region, and the location of the image charge equals to yj. So if we do that, if we add the image charges, we have a potential solution. We propose that the potential inside of the region, in the region enclosed by sigma, is going to be the sum of the potential of the real charges and that of the fictitious charges. It's a very simple problem because it's a scalar sum of individual potentials of point charges, right? So what we have to prove, suppose that this solution matches the boundary condition on sigma, right? If this is the solution, so we have to calculate the Laplacian of this proposed solution here and show that the Laplacian gives the charge distribution inside of the boundary, right? So let's check. The Laplace equation specifies that the Laplacian of phi equals to the charge density in the domain that we are considering. Well, the charge density is simply a set of any point charges, each one represented by a single delta function as the density, with a weight qi, and that's Laplace's equation, Poisson's equation, right? Laplacian equals to minus 1 over epsilon times the density. We are assuming that this solution here, that is the sum of the original potential plus image potential, matches the boundary condition. Okay? So, match the boundary condition. We have to prove that the proposed solution also satisfies the the Poisson's equation in the domain. So let's calculate the Laplacian of this proposed function. So if you calculate, the Laplacian goes directly inside of the sum of the real charges, and the Laplacian and the image charge is going to be the Laplacian of these inverse functions, recalling that location of those fictitious charges, image charges, is outside of the domain. So in the domain, which is the region enclosed by sigma, this will be, in fact, minus 4 pi delta, right, of x minus yj, but yj is outside of the region, and then the delta function is going to be 0. So the contribution of the image charges to the Laplacian is 0. On the other hand, the inner charges, they have a delta function associated with the Laplacian of the inverse function. And this this delta function picks up at the location of those charges. So they have those high densities, then 0, then high density 0. So these are all, in general, depending on the location inside, they might be 0 or not. So it's going to be a delta function. So it means that when you end up summing the two Laplacians, the end result is that the Laplacian is equals to the density associated with the real charges, which is the this, on the right-hand side of the expression here. So, 1, Laplacian of phi equals to the given density of charges. Second, potential on the boundary surface is equals to phi 0 by construction. We said that we found the image charges, so we equilibrate the potential on the boundary, right? So that's the idea. So the idea is to find image charges, values. You can have multiple image charges. You can have problems in which you have one real charge. Depending on the configuration of the boundary, you can have multiple image charges. You can have situations in which you have just one single charge and one single image charge. Each case is one different case. Okay? So let's look at some situations that they are not exactly the method of images, or in which you can consider those situations as the method of images in which the image is at infinity, right? So we have one image charge, but at infinity. So it's like no image at all, right? So we have here 3 situations. First one, you have a charge on the center of a system enclosed by a spherical shell, a conductive shell, which is grounded. That's the first case we are going to consider, right? Let's call it case A. Second case is a charge enclosed by a conductive spherical shell set at a constant potential V. It's a little different, right? And then finally, you're going to consider the last case. You have a charge, point charge, and you have a conductive surface, a shell, which is loaded with a charge Q, capital Q. So there are 3 different examples. They will serve for us to understand a little bit on what shielding is and how this is going to reflect as we advance on the method of image of curved surfaces. Okay. Let's look at this problem here. We are going to classify to separate regions. Inside is region 1, outside is region 2. Okay. So the first problem, let's call it problem A, right? We have, you know what I mean? You have spherical symmetry, correct? So it means that the potential is a function only on the distance to the origin, and the general solution is something like A plus B over R. Okay, so we have region 1, we have phi 1 equals to A plus B over R, A capital A. Inside, that's the general solution, and outside, solution is something like C plus D over R. Now notice that outside, I have here, let me just make this a point charge here in the center. Here the potential is grounded, right? So the solution outside if we make it r equals to a, right? So I have one equation, c plus d over a equals to ground, 0. Also, I will impose that the potential at infinity is 0. There's no electrical activity outside. So c plus d over infinity, which is 0, equals 0. So we have here c equals 0. Then, if you go there, d equals 0. So outside, the potential is always 0. No electrical activity outside for a grounded sphere, and the potential set at infinity, at 0 at infinity, right? So the potential outside equals to 0 anywhere. No electric field outside. And the potential inside, well, it's just a combination such that the potential is 0 so inside the potential is such that is that due to a point charge? I mean, we could calculate using Poisson's equation. We did that already, right? So if we just had a point charge in an open region, that would be Q over 4 pi, I think. Yeah, I'm assuming that the permittivity is that of vacuum, epsilon 0. So it's 4 pi epsilon 0 r, single charge. But the potential has to be 0 at r equals a, right? So the B in this example here is Q divided by 4 pi epsilon 0. We have to find A such that the potential goes to 0 at R equals A. Just subtract Q over 4 pi epsilon 0 A. You have the solution, right? That's the solution of the potential inside. There's a traditional solution plus a term that guarantees that the potential is 0 on the surface. It's interesting to see what happens outside. I mean, I solved the problem inside, placing the charge in the center, right? There's some interesting things that we have to look here. That's the result here, okay? And outside, potential equals to 0, right? So field outside equals to 0. Inside we have a field equals to minus gradient of phi, 1. You can calculate that, right? I'm not going to calculate it. Now, look at what happens. So the first remark is this. I mean, there is no electrical effect outside due to the inner charge. It means that I can move around my charge here. I can put the charge anywhere. Nothing is going to happen outside, because outside the potential is always 0. Nothing is felt outside. I can move the charge inside. So I'm shielding the outside because I grounded the potential, right? How exactly is this possible, right? Notice that, let's look at the shell has some thickness. It's a conductive material. We know that the field, static fields inside of conductors is always 0 for equilibrium to be set. So we have a density in the inner surface of the conductor, which is the surface here, right? Outside we don't have electric field, so outside on the outer surface of this the small region of thickness, small thickness of the spherical shell, on the outside surface there's no charge, okay? So even though we have charge inside, let's say plus charge or minus, depending on the sign of the Q, This can be a negative charge here. There's no charge on the outer surface. I mean, in fact, the charge is to be set inside in the surface here. Let's say the Q induces a negative charge, and that can be calculated with the charge density. But you see, I mean, there's no connection, nothing, there's no field line that goes from here to there. In other words, or vice versa, like this. Because there's no field inside. Whatever happens, whatever redistribution of charges take place in the inner surface, okay, if I move around the charge inside, the inner charge distribution can move around. I mean, this charge here, they can be, you know, we are going to demonstrate that when we go to spherical surfaces. If you go, you know, we have here, that's the outer surface, you have some charge distribution. I have just charge Q. If I move Q here, this thing is going to redistribute on the inner surface, but nothing is going to happen outside. Right? So that's what the solution of Laplace's equation, and Poisson's equation equivalently, yields. So outside, the external charge is 0, no field outside. And inside, the charge density on the inner surface of the shell is minus the normal component of D. That's a boundary condition, right? So the boundary condition on a conductor specifies that if you have the normal component pointing outside of the conductor, the charge density on the surface charge density is the n. In our case, we have the normal. This is, you know, this is the radial coordinates. So the normal component that points outside of the conductor is minus dr. So we just have to calculate dr at r equals a. So we know that E field equals to minus gradient of phi, right? If you calculate the gradient, it's going to be Q over 4 pi epsilon 0 r squared AR. And the D inside, the density, flux density vector, is epsilon 0 E1, which is Q over 4 pi r squared AR, and at r equals to a, d1 equals to q over 4 pi a squared d1, right? So minus the d1 radial equals to the charge, the surface charge density, which is going to be minus this number here, right? So we have that rho s equals minus q over 4 pi a squared. So if you have a positive q, the charge, the induced charge density on the inner surface is going to be minus q over 4 pi a squared. If you calculate the entire charge on the inner surface, it's going to be rho s times the area, because rho s is constant. So the induced charge is equals to minus q, right? So that's what we have, interestingly, right? The induced charge equals to minus q, and the external charge is 0. So it means this, if I have a shell, right? If I pick a charge, so I mean the shell has some thickness. I'm going to put here some thickness. Maybe I can do that like this. Hopefully it's going to make a nice round. Yeah. So if I have some thickness there, right? So if I have a charge here, so I can move around the charge, right, inside. Can move it around. nothing happens outside. No electrical activity outside. I can redistribute, right? I can come with the charge very close here. I can induce a lot of negative charges close. We're going to calculate that, then less negative charge far away. You have a non-uniform distribution of charge inside, but nothing happens here. That's very nice. That's shielding. Okay. In the second case, the second problem is that I'm sure here is this one here, right? Just show it in more detail. Now we have a little difference. The potential is not grounded, but is at the potential V. And again, I have a charge at the center. So now we have some activity outside, okay? Because potential now is V on the surface, goes to 0 at infinity. But notice, these are separate problems. The outside problem has nothing to do with the inside problem. Due to the uniqueness theorem, right? Solution in a domain only depends on the potential imposed on the boundary of the domain and on the charge distribution. So whatever I do outside here doesn't affect what I have here, okay? Right? So the solutions are independent. I solve the problems independently. So inside now, I just have to change the constant so that the potential gives V on the boundary. So we are going to have a solution that is like this. I invite you to do this calculation. So outside is very easy. The potential falls off with 1 over R, right? Potential is something like this, constant over R, right? And potential at R equals A, so that's phi 2, right? Equals to V. So B over A equals to V, so B is given by V times A. So the solution outside equals to VA over R. Now we have electrical activity outside. This electrical activity doesn't depend on the charge inside. You see that this function here only depends on the value that I impose for the potential on the surface, which is V, right? You can calculate the charge outside on the outer surface. You can calculate the field, which is going to be VA over R square AR, which is the gradient, right? Minus gradient of phi 2, gradient of phi 2. The derivative is 1 over R squared minus times minus plus VA over R squared AR. The flux density vector is simply epsilon 0 E. And then we have the rho S, I'm going to say rho outside, right? The surface density right outside on the outer surface, let's call it rho SA. This is a negligible, this thickness here is much less than A, so it's negligible difference between the inner and outer distances from the origin. So it's just a matter of rho out, let's call it like this, rho SA. Let me just let's do like this, external, rho s external, okay? So the rho s external is just the outer components, the component points outward from the conductor. It's going to be just calculate that at r equals a, so it's going to be epsilon 0 VA over a square. So it's going to be epsilon 0 V over a. So the external charge, the charge is uniformly distributed outside with the total charge times 4 pi squared is going to be 4 pi a epsilon 0 V. That's the total charge on the outer surface. Has no connection with the inner solution. Okay, if we go inside now, this is the solution you just got, right? Inside, well, just add a constant to the previous solution. The previous solution is the one that gives 0 on the boundary, so you just add V. So now the potential is going to be V at R equals A. So you can see that again, because those parameters, they have 0 derivatives, they do not contribute to the charge density on the surface. Charge density depends on the normal component of D, which is proportional to E, which is the derivative of V, of the potential. So again, I have just to make a derivative of this function here. And then we have the internal density is exactly the same. Induced charge equals to minus Q. Okay? So that's the charge outside. I think I'm missing here an A here. There's a small mistake here. Yeah. We forgot to add a here. Right? So that's how it's supposed to be. I forgot to multiply by the, 4 pi a square. So you'll have an additional a. So you see, outside we have a uniform distribution of charge. Inside for this problem too, but also again, what happens? Oops, what happened here? This is outside of the boundary here. Again, what happens is that outside we have, let's say, try to raise this thing here. Raise this. Okay. Where is that? Here now we have outside, we have a charge Q, which is 4 pi epsilon 0 VA, uniformly distributed. Let's assume that small k, lowercase k, is positive. Let's say that outside we have a charge like that. Well, this charge here depends on the sign of V, right? If V is positive, let's say V is positive. So here we have, let me just amplify that a little bit. So here we are inside of the shell, right there, okay? Uniform distribution. Okay, we have that. And inside we have a possibly, let's say that Q is negative, is positive. So inside we have charge which is negative, induced charge which is negative inside. You see that the same conductor has on one side negative charges which are induced because of the inner charge, and outside you have negative. At the moment that I have a charge on the center, this charge here, the blue ones, they are distributed uniformly, but I can also move this thing here. I can move it around. I'm going to rearrange the location of the inner charges. But the outside charges are going to remain uniformly distributed. Nothing is going to change outside. The field outside is always the same, only depends on the potential. No influence of the charge on its location. Okay? So that's very important to understand the concept of domain of a solution, right? It means that, the solution in region 2 only depends on how I impose the potential in the surface and the potential at infinity, and whatever happen outside. I don't have charges outside. So whatever happens inside, nothing's going to happen outside, because outside the problem is governed by the potential that's given on the surface. And the potential at infinity assumed to be 0. So nothing happens if I change inside the conditions, because there's no connection between the two solutions, okay? Now, in the third example here, let's assume that we have the third problem is a problem C, right? So we have, sorry, make a drawing here quickly. We have the spherical conductive shell. We have a charge inside at the center. Now we are, the charge has a total charge Q, right? We can solve again the problem. We don't know the potential on the surface, we know the charge. But let's say if I apply Gauss's law, if I pick a concentric sphere and calculate the Gauss's law, right? So I can easily demonstrate that the field outside is that due to a potential given by Q plus Q over 4 pi epsilon 0 R. Why is that? Well, there's a potential that falls off to 0 at infinity, right? If I use Gauss's law on a spherical Gaussian surface, it means that the total flux equals to the total enclosed charge, but the enclosed charge is Q plus Q, right? I'm saying that the surface here has total charge Q. So the total charge enclosed by a Gaussian surface is Q, capital Q plus lowercase q. So the potential has to be something like this, because it falls off to 0 at infinity and gives the correct flux density outside, right? What's the solution inside? Well, so you ask yourself, what is the potential of the surface here? Just calculate. The potential is V equals to Q plus Q over 4 pi epsilon 0 A. So the solution inside is that gives me a potential V on the spherical surface. So it's going to be this term here, right? Plus that solution that gives us 0 potential, which is Q over 4 pi epsilon 0 1 over R minus 1 over A, right? So that's the final solution inside. That's the solution inside. That's the solution outside. Notice what happens. Again, the induced charge in the inner surface of the spherical shell is Q. Is the term that gives a variation as a function of R. Okay? These terms don't contribute to anything when you try to calculate the charge density. So inside the induced charge, let's say K induced inner surface equals to minus Q. Well, if the charge is, if this is the total charge is Q, it means that the charge on the external side of the surface Q plus Q, because the total gives capital Q, right? We can calculate that. I mean, just look at this one, right? That's the term that appears here. That's the one that's going to give the total charge on the outer surface. So that's what happens now in this case. Oh, there's another error here. So the external charge density is Q plus Q, right? Not Q minus Q. So we have a uniform distribution outside, right? On the outer surface, right? So that the total charge outside is Q plus Q. Inside I have an induced charge minus Q. And the total charge is going to be, on the surface, is going to be Q, capital Q plus lowercase q, small q, minus small q, which is going to give capital Q, right? Again, same thing, right? I mean, nothing is going to happen if I move my charge. Let me move this to another page here. Paste. And just draw another. I mean, let's make a little thicker now. I'm going to do that. I'm going to increase a little thickness of this shell here. So whatever happens, I have the charge inside, right? So it induces the total charge minus Q, and outside the total charge is Q plus Q. So the total, I mean the net result is capital Q, right? So whatever I do here, I can move around this. When I do that, I'm going to have a non-uniform, right, charge distribution inside. But outside, the thing still remains the same. I mean, the total charge outside is Q, capital Q plus lowercase q. But the charge outside is always uniformly distributed because the problem outside has no relation with the problem inside. So that's again shielding, right? You have an effect, but it's that true uniform distribution that doesn't move around like the one inside. So outside I have a uniform distribution, which is not connected to anything that happens inside. Okay? So these are some interesting details that we have to get familiarized, and they are related to the properties of the solution of Poisson's and Laplace equations. I mean, uniqueness of solutions, independence of solutions on different boundaries. A solution depends only on what the potential, how the potential is set on a boundary that includes the domain and on the charge distribution inside. So that's a clear demonstration of this principle, right? I mean, outside, right? Whatever happens inside is not going to affect my solution inside because I'm giving the conditions outside, right? A uniform distribution of charge with a total charge capital Q. So that's what we wanted to talk regarding shielding and simple problems involving a point charge and a conductive surface. This was a high symmetry problem, okay? Now let's move on to consider now a point charge near a planar conductor, as in this draft this drawing here, right? We have the entire surface at z equals 0 is grounded. So, I mean, whatever happens at z smaller than 0 doesn't matter. I can just have a sheet of a conductor which is set at the zero potential. I can have a lot of things happening down, below the ground, below z equals 0, but that is not going to affect the solution above the ground. So, I mean, in fact, I'm going to find the solution in the upper hemisphere, given the potential at this problem. You just have a grounded surface. And the question is, what is the solution, right, above the grounded surface? So the idea is to try to include an image charge outside of my domain. Outside my domain is the region z smaller than 0. So we're going to try one single charge. By symmetry, I mean the image charge is located on the z-axis, okay? So, I mean, RAR is a vector on the plane z equals 0. We are going to include this charge. To be very general, let's assume that the charge has a value q prime and a location which is minus d prime. So the distance of the image charge to the origin equals to minus d prime. The original charge has a distance d. Now the problem is, the question is this: how do we choose q prime and d prime so that the potential on z equals 0 is 0? Right? So the solution at z equals 0, the proposed solution is that's due to a potential of the original charge plus its image in vector form, right? X minus the location of the charge equals dAz, x minus the location of the image charge, which is minus d, right? X minus d prime az. So it gives a plus sign here, right? Well, first consideration is that the potential has to be 0 at z equals 0. And of course, the potential is going to involve the sum of two terms. These are positive, definite, right? So it means that the sign of the image charge has to be opposed to that of the original charge. So first condition is that QQ prime is less than 0. Now let's calculate those magnitudes, right, using vector algebra. Well, you can use here x equals RAR plus ZAZ, right? That's general vector, right? So if I have that minus DAZ, you're going to end up with that quantity. Same thing for the other magnitude. So when you solve that, you're going to have something like this. Do a little bit of calculation here. So you're going to have something like this. It's Q divided by 4 pi epsilon 0. The magnitude is 2.5, right? R squared plus D squared 2.5. This is at Z equals 0. Plus Q prime divided by 4 pi epsilon 0 R squared plus D prime square equals to 0. Then we move this to the right hand side. It's going to be equals to minus. Then I can square both members. You're going to end up with Q squared the sign goes away, so it's q prime square r square plus d squared 1/2. Sorry, no 1/2 here. And then we rearrange and have q square minus q prime square r square plus d square minus d prime square equals 0. So we're doing this because we're going to use this as general method, right? We end up with a function of a of r, which is 0 whatever is r. It means that a has to be set equals 0 and b as well. So it means that q square equals to q prime square and d square equals to d prime square. Now, the solution here is q equals to, or q prime equals to plus or minus q, right? And d prime equals to plus or minus d. But recall that q prime has opposite sign, has a sign that's opposed to that of q, so q prime equals to minus q. And also, d prime has to be positive because you have to put the image charge outside the domain. So d prime equals to d. So that's the solution. With that combination, we have a zero potential in the z equals 0 plane, right? So is this the right solution? Well, let's look at the solution after we do that substitution. That's how the solution looks like. Right? So we have a minus here. Q is factored out. And here you have z minus d, z plus d. So potential at infinity goes to 0 as originally stated. Potential at z equals 0 is 0, right? Because this term equals that one. So this whole thing goes to 0. And the Laplacian of the potential, right, is going to be that due to a point charge at z equals d, which is going to be minus 4 pi delta function of x minus zaz, because the other doesn't contribute to anything on the upper hemisphere. So one important question is that of induced charge on the surface, right? What is the induced charge? Well, as we derive the boundary condition, we have a conductor. The surface charge is the normal component of the flux density vector that points outside of the region, to the region, right? So it's just a matter of calculating Ez, which is equals to minus d phi dz, and calculate that at z equals 0. Then we multiply by epsilon 0. We have this component here, right? So that's what we have to do right here, the outline of the calculation. Just a matter of calculating the derivative of a function of z. So that's for you people. So when we do that, we obtain a function, right, that changes or varies with the inverse dependence of, root square to the cube of squared distance on the plane. R over d gives a measure of how far away relative to the height, right? R over d equals 1 means that you are on a circumference equals to the same distance of the charge to the surface. So things happen if I move the charge close to the surface or away from it. If I move to the surface, the induced charge gets more intense right on the shadow of the charge and gets less weaker, vanishing out as we move away from that. So it means that you see here that at r equals 0, the charge density, which is the peak, right, magnitude of the magnitude of the charge density, equals to 1 over d square, as d, as you approach the charge to the surface, you get more intense. You have a very, very sharp charge density right below the charge that you have. If you calculate the integral of this function, you're going to have, on the surface, right? Surface element equals to r dr d phi. So it's just a matter of integrating, right, on r from 0 to infinity and on phi from 0 to 2 pi. So you get a total induced charge of minus q, right? How can that be, right? Very nice. In some curved surface, this is not the case, but for a planar surface, that happens. So let's see how Gauss's law explains that. Let's put here. I think I talked something about that earlier. We have the surface here. We have that's the we have the surface there, right? Then we have a charge. Sorry, a charge. Well, the E field, remember that we have a fictitious image charge here. The field lines, they are exactly the same field lines that if you extend the line, it's going to end on the charge. So this is a dipole, in fact, right? So I have a curved line like this, going to end there, right? It's going to end on the surface, but if you extend the line, it's going to end on the image charge, and so on, right? All the lines go down, and there is one line that goes like this, right? But it arrives like this, here. One line only. There's an infinity number of lines, but only one line goes there, but it arrives here, okay? On this arrives here. If I get a Gaussian surface around this charge, whatever form we have, the total flux is going to be q coulombs, right? All the lines that leave the surface here, they end up on the image charge or end up on the induced charge. So if I get a Gaussian surface like this, let's make like that, like this, Gaussian surface like that, right? So in fact, there's no charge, there's no line, there's no field, in fact. There's no real field here. Field here equals to 0. So all the flux is that on the upper part of this green surface here, Gaussian surface. All the q coulombs, we're going to transverse this green surface here and end up on the grounded plane. So the induced charge is going to be minus q, right? Flux conservation, charge conservation. So you can calculate that by integrating. You're going to have that value. Let's just take a look here quickly. Here, quickly here. So here we have an idea on what happens on the charge density on the surface. This is a plot of minus the charge density, right? That's what we are doing here. Let me just show you. making a plot of minus rho s versus r. Okay, when r equals to d, we have just see what am I plotting here, times x. Yeah. So yeah, this is not a relative value. So the value of these is giving is shown in this window here, 0.01 this example. So I'm very close to the surface. So if you look, I mean, the density is the minus rho s. It's very high, right? I mean, I have to go all the way there. Let me get a little bit so you can see it. Max. Oh, sorry about that. I'm doing the wrong one. So if I magnify the up, okay. So I have the maximum density here, right? Because I'm very close to the surface, very high density. As we move away, right, the density, peak density decreases. And also, I mean, notice that here, you see that the distance r is absolute value. So I'm going to see where it falls to half of the maximum. You can see here, right? At a distance, I mean, we are only a very small region below the surface. This is 250, something like this. At 0.03, you know, let's say meters, you have the density falls to 1.5. As we move away, right, from the, put the charge, move away from the surface. So the charge starts distributing more and more. Okay, now we are going to have, let me just see it. Sorry about that, just here. Let me pick, well, now it's distributing, you know, it's spreading more, right? Now I'm trying to control here, there. So here now the charge goes over a region. Here falls off to half, almost at 0.3, right? If I go even further, far away, I start to spreading even more. Let me just reduce the magnification here. I put manually here, 10. Put 20, 5. Put 5. Now, so it falls off to a half here now at 0.4, right? So as we move away, the charge distribution, the induced charge distribution spreads out. Total charge is always minus Q, right? And if we move closer to the surface like this, charge density starts to peak, and it starts to concentrate very close to the origin, right? So that's what we got. Very high density, nothing happens far away from the origin. Let me just increase a little bit here. Okay, there. Okay. Very well. Also, it's a very simple method to demonstrate that the force, right, is the same as the force between charge and image charge. The force that the plane exerts on the charge, or vice versa, is that between the charge and its image. Well, it's not difficult to show, right? We have this. We have here the boundary. Have that. Then, if you look at the situation, I have the charge. So it's like, I mean, it's the same as if the charge is in the field of the image charge. So the image charge is just a field, right? So the force, the image, the field due to the image equals to the force Q times E, right? So in fact, this field is not pointing out up, it's pointing down. So in this case, I mean, let's assume Q is positive. So the image charge is exerting a field, right? I mean, the field lies like this, right? But I mean, the field on the combination, the field of the image charge on Q points downwards. You remove the charge and determines the field of the image charge on the location of the charge. It's going to feel something like this. And this image field equals to the force of the image charge divided by Q, right? So I mean, it's the force between 2 point charges. So in this case, it's going to be, so the force between them is going to be attractive, right? So the force is going to be product of the charges, Q squared, 4 pi epsilon 0. The distance is 2d square minus az. So it's attractive force. So the force between charge and surface and the conductive surface. So the plane pulls the charge with a force which is given by Q squared minus, right, 16 pi epsilon 0 d squared az. That's how the plane pulls the charge, right? Let's move a little faster. So I mean, now we can solve Poisson's equation, any problem involving an arbitrary charge distribution above in the upper hemisphere for a grounded surface at z equals 0. Suppose that we have, a charge distribution like this, right? So what we do, we construct an image distribution picking point by point of this, you pick this point here, you find an image at the symmetrical position, and we get that point there, you find this symmetrical position in that point, and so on. And we keep, go here, the image charge right here. Then we keep assembling the image charges. So in this example, the image distribution is going to look like the mirror image of the original charge. Location of the corresponding element for an element dv prime, have a dv prime here. You have an element corresponding that is located, just a matter of reflecting this vector here to that one. That can be done just by, you see that the distance of the point to the plane z equals 0 equals z prime. So this vector here is 2z prime. So you're going to have, you see, let me just draw here so make it easier. I'm going to draw in a, a vertical position. You have something like this, right? So if this coordinate is z prime, so this vector here is going to be 2z prime az. It means that the location of the image volume distribution is x2 prime. when I sum 2z prime az, I get x prime. So if I have a dv prime volume, right? So location of this dv2 prime, the image volume element, is going to be at this position x2 prime equals to x prime minus 2z prime az. So when doing the image method, it means that when you have a charge rho of x prime dv prime, that gives a corresponding image rho x prime dv prime minus. So it means that the corresponding image, the potential for two elements, the original bar plus the image would be something like this. It would be dv prime rho of x prime 4 pi epsilon 0 x minus x prime, and the image would give plus rho image x prime dv2 primes divided by x 4 pi epsilon 0, right? Or epsilon, right? If you have a homogeneous medium, it could be epsilon. Let's put the epsilon 0, just replace by epsilon if required. Now the prescription is this: x2 prime has to be given by this expression, and the charge, when I integrate, let's move that to the next page. It's important to show in detail this thing here. Copy. Then I calculate the potential by integration on both volumes, right? So the potential is going to be integration on V plus the summation on the image distribution. Is going to be, let's call it V prime. V prime is the other volume. It's going to be dv2 primes rho image x 2 primes, right? Now what do we do? We have to do a change of variables, right? So that rho x2 primes times dv2 primes has to correspond to the image method result, which is the minus of the charge on volume v prime, dv prime. It's minus rho x prime dv prime. So I have made a change of variables. I'm integrating on v prime. Let's make a v2 prime here, so that we with the same notation of the location x2 prime here, right? So this equals to that. So it means that I'm changing the variable. So I'm integrating now in v2 prime. I change the region of integration to the integration on the upper volume, v, right? What else? Well, x2 prime has to be set to x prime minus 2z prime az. So that's how you calculate the potential. It's two integrals on the same volume. I'm going to put epsilon, right? Let's assume the upper median has a permittivity equals epsilon, x minus x prime, plus the potential of the image charge is the same, the integral in volume v, dv prime, right? Rho x prime, because that's the image result, 4 pi epsilon, x minus x prime, plus 2z prime az. Let's move this to the left. That's the results we have. So we solve now Poisson's equation on the upper hemisphere. Where is the integration carried out? Well, the integration is carried out on the volume of where we have a density, right? That's where the integration is carried out. So on the V prime, this is rho x prime. So that's how we do it. So we have solved one specific case of Poisson's equation in which the potential is grounded on the z equals 0 plane, right? So here we have some examples to show what happens for different charge distributions. For instance, this example here is interesting for antenna, right? Antenna is on a simple dipole antenna, just a piece of wire on a grounded plane. Has a certain length. The amount of radiation depends on the relative size of the length to the wavelength of the radiation that you consider. So it's important to know how, because the antenna looks like a dipole, right? That can be, that's studied in radiation, in the course of antennas and radiation. We are going to, not in this course, we are not going to talk about, we are going to talk about homogeneous wave equation, but not on specific radiation patterns. But is for the course of PGEE937. We talk about that. But let's see, suppose that we have a dipole, right? A dipole which is tilted like this, right? The question is, how do I solve? Suppose I calculate the dipole field, right? We know we have to way of calculating the asymptotic behavior. Let's say that the distance of the dipole here is much larger than the size of the dipole. We could calculate that asymptotically. So suppose we have a grounded surface. So how do we solve the problem outside, above the plane? Well, we have to find the image of the dipole. Now recall that the dipole has a head which is positive and a tail which is negative. So here, if you make an image, we're going to have a minus here and a plus here. So we have a dipole image like that, right? So that's how it is. So that's what is the image. So the image of a dipole like this is a dipole tilted like the mirror image. Head has a tail as an image, tail has a head as an image. So for instance, if you had a dipole like this, the image is a dipole like that. So it's you zero the effect. On the other hand, if you have a dipole like that, the image is a dipole like this. So I have a twice as long dipole, twice as strong dipole moment. So in fact, that's what happens. If you have an antenna, a piece of wire on a grounded plane of length L, that's equivalent to a 2L long piece of wire. So these are immediate consequences of this principle. Here are some additional examples. Let me stop this here. I'll just do this thing quickly here. I don't need that anymore. Just 1 minute. Lecture 11. Second. Simulation, right? Simulation, okay. So if I have a, polarized plate, circular plate disc above a grounded plane, so we have lots of dipoles, right? All like this, a line up like this. So we have a polarizable disc. So what's the image? Well, it's the image of several dipoles. We're going to have something like that, right? So we can solve the problem above the plane by calculating that the potential due to a polarized disc plus its image, which is something that also points upwards. Okay? Very well. So now we have solved the potential, Poisson's equation, what we did so far. Using method of images. What do we have? We have the problem of a plane surface with arbitrary charge density, but now we have only a grounded plane. I have solved Poisson's equations for a grounded surface, right? So we have the solution of this problem, this immersed on a homogeneous medium, subjected to the condition phi equals to 0, right? Let's now construct the Green's function for the problem, which is that due to a surface at z equals 0 with an arbitrary potential distribution. So to solve Poisson's equation. To do that, we have to solve Green's function for the problem of in the upper hemisphere, giving the potential at ground at the z equals 0 and the potential equals 0 at infinity. That's let's solve the Dirichlet boundary value problem, right? So let's just recall that if we have, you see that Green's function is nothing less than the solution of the point charge on a grounded surface, right? Because that's what the Green function is. If we imagine that we have a point charge of value 4 pi epsilon on the surface, that will give, we're going to have an image minus 4 pi epsilon, located at x prime minus 2z prime az, as we just did. So the Green function for the Dirichlet boundary value problem is that is 0 on the surface that limits the domain, right? There are two surfaces, z equals 0 and one imaginary sphere at r going to infinity. So, so the Green function for the Dirichlet BVP is that which is 0 on the z equals 0 plane. In other words, for x prime equals to r prime of cylindrical coordinates ar, and equals 0 at infinity for large r, right? And the Green function satisfies this equation. So if we use a point charge like this, the problem we just solved can be used to use this Green function. So the Green function is something like this, right? Inverse function, and the other function that makes the potential equal 0 at the ground surface. So notice that here z equals 0 means magnitude of x minus x prime equals to magnitude of x minus x2 prime, right? Because x2 prime equals to x prime minus 2z prime az, and those are equal, not equal, they are equal, exactly, yeah. X prime equals to x2 prime at z equals 0. So the Green function is 0 in the, this function is 0 at z equals 0 and at z going to infinity. So that's the Green function for the boundary, for the Dirichlet boundary value problem. And then it means that this general solution, we found the Green function. That's what we need to solve any problem, right? The recipe is this. The potential is equals to this kernel here, rho times the Green function for the Dirichlet boundary value problem, minus potential given on the surface, potential at infinity equals 0, so the integration is carried out on the z equals 0 plane. All we have to do is to calculate this normal derivative on the this normal derivative on the plane z equals 0, notice that the normal coordinate is the projection of x prime along the normal direction, which is directed outwards, right? The normal component is outwards the region, so it's minus az. I'm going to show you how to do it, okay? So if we plug JD in here, we have the solution. Let's see how it looks like the normal derivative. At z equals 0, the normal coordinate is x prime dot minus az, which is equals to minus z prime. So the derivative relative to the normal is minus dg dz prime, and has to be calculated at z equals 0. Okay? So that's how the solution looks like. So have the contribution of one term of the green function, the other term is like the potential of the image distribution. There's some additional information here, which is depending on how the potential behaves on the surface. Okay, that's the term. The surface integral is here, right? Well, if the potential is grounded at z equals 0, so this is going to be 0. So this term here goes away, right? And the solution is going to be the same one we obtained using the method of images. There is no surface contribution. Okay? If we have to calculate the derivative of the green function, well, we have to go, have to calculate. If you look at the formula here, let's take a look at that, right? How do we calculate this thing here? Notice this is going to be a function, right, of the coordinates on the surface. So this has to result as a function of r and also as a function of z, r and z. So let's show you how to, I will just outline how to calculate the derivative, right? GD equals to 1 over x minus x prime minus 1 over x minus x2 prime. What we want? We want dgd dz prime, and also at z prime equals 0. So that means az prime, az, right? Dot gradient of jd at z prime equals 0. So that's what we want. You see that x minus x prime in rectangular coordinates is like this, the magnitude square, right? X minus x2 prime is given by this square, right? Square plus y minus y2 prime square plus z minus z2 prime square. Let's call this function equals to f, and this equals to g. Okay. Recall that x2 prime equals to x prime, y2 prime equals to y prime, and z2 prime. So recall that x2 prime equals to x minus 2z prime az. So it means that z2 prime equals z, sorry, it's not that. It's minus x prime plus 2z prime az. So z2 prime equals to minus z prime plus equals to z x2 prime x minus x2 prime. I mean, in other words, z2 prime is minus x minus 2z prime az. So z2 prime is minus z prime. So g equals to square. Okay. Now that we have, there we have. So dgd dz equals to 1 over x minus x prime to the cube, right? Derivative relative to z prime, right? It's going to be that times, if you do the calculation, it's like this. Let me just do the other way, like this. Instead of doing that, it's 1 over, I mean, is do this. Delete that. Is d dz prime 1 over f to 3/2. That's right, right? Minus d dz prime of the function 1 over g to 3/2. This is right. No, not right. It's 1/2. Sorry about that. It's 1/2. 1/2. That's what you do, right? Right. So this is gonna be 1 over f to 3/2 df dz prime. Sorry. So that's the derivative f to minus 1/2. It's minus 1/2 of 1 over f to 3/2 df dz prime. Right? So minus minus is plus 1/2. 1 over g to 3/2 dg. It's a partial derivative, but never mind, just whatever, right? So that gives me so notice that at z equals 0, z prime equals 0, f and g are equal, right? So it's 1 over f to 3/2 at z prime equals 0. So df dz prime, there's 1/2 right there, right? 1/2. Df dz prime equals to 2 times z minus z prime times minus 1 at z prime equals 0 equals to minus 2z. So minus 2z with minus 1/2 is going to be 1. So it's going to be z, right? That's what happens for the first term. The second one is going to be plus 1 over 2 f to 3/2 at z prime equals 0 times dg dz prime. dg dz prime equals to 2z plus z prime at z prime equals 0, which equals to 2z, right? So it's going to be 2z here. So the result equals, this cancels out. The result is going to be 2z divided by f to 3/2 at z prime equals 0. So it means that the derivative dgd dz prime at z prime, sorry, that's the element you have to put there, equals to 2 times z x minus r prime a r prime, which is f 3/2 is this magnitude to the third power. So that's the derivative you have to include in that integral of the green function. Okay, so that's the result we have. Let me just check that's correct. So that's what we have to include in this term here, right? The derivative is given by that function there. 2z divided by x minus r prime, a r prime. This is a function of, remember, x equals to r a r in cylindrical coordinates plus z a z, right? So this versor is not the same as that one. They are different things. Okay? So with that, we conclude our lecture. Today was less than 2 hours, could be even less, but I lost some time here doing some derivations. But then we conclude this class, today's class. I hope to see you next time. Bye-bye.